Very good. Well, thank you all for joining us. Especially thank you for joining us given the weather today, and that it's not the most pleasant night outside, but really excited to have everybody here join us for this meetup. We're going to be talking tonight about turning data into meaningful insights. We've got a few great presentations planned. But our hope is that the presentations spark conversation and discussion, so definitely let us know if there's questions and we can carry on the conversation beyond the presentations. I guess just a brief introduction. My name is Salim Sawaya. I lead Esri's nonprofit and global organizations team. I've been with Esri about coming up to 15 years now, based here in DC. There's a team of about 10 of us within Esri who specifically focus on working with nonprofits, foundations, UN, other international organizations, the USAID, and other US foreign assistance agencies. As many of you probably know, Esri has been in the business of geographic information systems for, will be 50 years next year. It's in our DNA to support and work with nonprofits and organizations doing good in the world. Part of our mission is to help organizations have a bigger impact using GIS and location information and location technologies. And that's where a lot of our work on our team is focused in working with organizations like all of yours. Tonight's presentations are planned from a couple of Esri colleagues whom I'll introduce, as well as one of our partners that works for the Chesapeake Conservancy. I'll introduce everybody now in a second, and then they'll kind of get into their presentations. It's just a little bit of housekeeping. If you hear an alarm going off, the emergency exits or the door you came through, if you do need the restroom, you go back towards the elevators, just past them, and you'll see the signs to your respective restroom. And yeah, once we finish up with the presentations, we'll continue on outside in the lobby and continue the discussion. So our first speaker tonight is our colleague Jerry Kim. Jerry is one of Esri's senior product engineers for Esri's imagery development team. He's based here in the DC office with the rest of us. Focuses on imagery capabilities across the ArcGIS platform. Jerry has more than 40 years of experience working in the imagery and remote sensing industry, focused on systems engineering, design, implementation management for both GIS and remote sensing systems. Emily Mills, who's on the line, I think she smartly decided not to try and drive from Annapolis down to DC with the roads. But Emily is a senior geospatial analyst at the Chesapeake Conservancy. They're a very close nonprofit partner of ours, working in the region and doing a lot with GIS and remote sensing. She supports Chesapeake Bay Program Partnership projects, including high-res land cover classification and landscape scale change detection. She also works with partners to leverage the Conservancy's land cover data and enhance flow path modeling to prioritize conservation and restoration opportunities throughout the Chesapeake Bay watershed. And last but not least, we'll be hearing from our colleague Alberto Nieto. He's a geographer, Python developer, and a spatial analyst who helps people use GIS to find innovative solutions to important spatial problems. Prior to joining Esri a few years ago, he worked for nearly a decade at Census, NOAA, National Weather Service, and Capital One. His work includes a focus on spatial statistics, our Python API, and other Python solutions, and contributing to some of our R&D efforts around spatial machine learning and artificial intelligence. So with that, I'll hand it over to Jerry to kick off our presentations, and thank you all again for joining us.
Well, good evening. Thank you. I want to talk tonight about our imagery capability in ArcGIS. Imagery is kind of a nice way to both gain synoptic information and immediate information. So, what does it mean? What does it mean to nonprofit organizations? Well, first of all, the world we live in is very dynamic. Things change in a moment. Within that moment, the data you have in your GIS may become outdated. That's true for the geopolitical situation, the landscape, the demographic landscape. It's also true of the environment. You need metrics to understand that, and imagery is a good source for that. But more important than that, imagery is also a very good tool for communicating. One of the issues that nonprofits have, scientific communities have, et cetera, is trying to communicate what they see, what they understand. And imagery also becomes that communication. There's a synergy between GIS and imagery. One is it provides context in both directions. If you look at a map, sometimes it's very sparse, you don't really understand what's going on. But you bring in the imagery, it gives you good context. Similarly, if you're trying to exploit the imagery, the GIS can provide that context to limit your search areas. When you limit your search areas, your statistics get better, learning ability gets better. And as a result, you can extract richer information out of the imagery. So finally, remote sensing is evolving. And I'll talk a little bit about how that's evolving, but we're going to kind of conclude this presentation with Alberto, giving you a look into where we're driving ahead with machine learning and AI to extract the information that we can visually see in the imagery so easily, but is sometimes so difficult to put into GIS context. So you've probably seen our new branding, right? Science. What does that really mean? As we walk down the street, depending on our background, depending on our interests, we have different views of what the world is. And how we interact with the world is really a very complicated thing. What we're trying to do in GIS is we're trying to bring all of those different views together by integrating a variety of different sensors. You have satellite data, for instance, with imagery. You get these very synoptic views of the world, but you may not quite have actionable information. Airborne, a little bit better. Drones are a way to get extraordinarily high resolution imagery under your own control when you want it. And it's making remote sensing more personal. But it's also driven by all this contextual information that we have with GIS. With the built environment, with the natural environment, there are hundreds of, maybe even thousands of in situ sensors that we can take advantage of. And as we pull those in through the Internet of Things, we suddenly have a very dynamic GIS, maybe one that's almost as dynamic as the world that we have to understand in order to derive good outcomes. GIS works with all kinds of data, right? Imagery and LiDAR are two remote sensing examples. We're certainly very familiar, if you've worked with GIS, with all the tabular data, vector data. And now, on an increasing basis, you see these feeds from real-time Internet of Things, from big data sources. And all of that can be visualized, can be manipulated, understood, analyzed, not just in a 2D context, but a 3D context. And so it makes for a very complicated technology, right? But it's complicated in order to hopefully make your work a little bit more direct and straightforward. Behind that is an architect. You think of where we were with GIS 15 years ago. We were basically desktops. And you'd come into work and you'd gather up data and you'd put data on your desktop, and you had this very insular world that you worked in, and people would come up to you and say, I have a question, do you think you could help me? And it's not a very efficient way for organizations to communicate. So what we've evolved to is an enterprise architecture. And sitting within that enterprise architecture, as a user, I log in and I see things like portal online, right? I can use that to authenticate that I'm who I am and what my privileges are. But I can also use it for discovery and acquisition of data. Behind that sits a series of servers. GIS server, very traditional. Image server, serving all things imagery, processing imagery. It's important to live in that environment, as I'll explain, because imagery is very large. You can't move it very easily. So you want to put processing near the image. Geo event server, what does that do? Well, it takes in these real-time feeds and allows you to express those in different ways across the platform. And finally, geoanalytics. very rich analysis on very large data. On the left side of the slide, of course, these are all your devices you get to use. Your traditional desktop, but also the apps. And you can extend all the way out into the field if you want, right? And that includes the imagery. You can push that imagery out, extend people's vision, if you will. So that's the architecture behind all this. We like to think of ArcGIS as a complete imagery platform. So we can manipulate and exploit imagery with a variety of tools. Stereo. You happen to have full motion video, you can exploit that. Do it in conjunction with the context of the GIS. Some of the work that I've seen done in Florida with their water management districts, very fascinating work using video to characterize habitats and some of the hydrologic effects that they're trying to manage within the region. We also, years ago, talked about this a little bit more, we forced everybody into a map presentation with imagery. That isn't very natural based on a lot of the imagery. So we have things like the image space capability. We have tools like the image analysis window within ArcMap, but also in the ribbon interface, we've got capabilities in Pro that let you exploit data, do image classification, image processing, change detection, analytics, and things that allow you to do charting, ortho mapping if you want to develop new base maps from the imagery. And of course, it works across a variety of sensors and a variety. So, as a user, there's also content, right? Thank you. You also have access to content with ArcGIS. You've got access to all the Landsat data within hours of it being collected, Sentinel-2, sea surface temperatures. Airbus, NAPE, NAPE imagery, of course, is collected across the United States, a third of the United States each year. And then Digital Globe, not only the imagery you have access to with premium services, but you also have analytics. And all that's brought to you by that architecture. Other things that are available in terms of content are things you find in the Living Atlas. Some of those are raw imagery and the likes, but some of them are Internet of Things, stream gauges, etc., base maps, which everybody uses. And products that users like yourself produce and put back into the Living Atlas. So it's a resource that really helps our ecosystem of users begin to do good work. Now, obviously that architecture supports things within the cloud. Relative to imagery, that means that I'm working not just with imagery itself, but point cloud data that's either derived from imagery or sourced from LiDAR data. And you'll hear within our dialogue with our users over the next couple of years, there's four main things that we can do with the imagery. We visualize it, we analyze it, we produce maps from it, and of course, foundational to that and driving that is the image management capability. This is an example of imagery that was collected after the hurricanes in Puerto Rico last year. Certainly it's interesting to look at the data that was collected, but it's more interesting to think about who had access to that and how, right? You have many terabytes of data here that was collected, was put into the cloud, made accessible to the users. What you're seeing is an app designed for both change detection and making observations. So on the left side of the screen, you see the imagery collected after the hurricane. On the right side, you see the imagery that was historical in nature. And you can see how the terrain changed in a matter of hours. But you have the ability to go in and make observations associated with this. So as a user community, people can go in, look at the data, and very rapidly assess what they're seeing in terms of impacts. So here we're bringing up a dialogue, and it lets you say, what is the property damage that I'm seeing? Who am I as an analyst? And what's the date that I'm making this observation of? Now, as I do that, it's entering data into a geodatabase, of course. The geodatabase is also shared as a feature service. And you might have many people going through and making these observations. Well, that's great. You want to be able to share that across the organization, is trying to make a difference in that landscape. So you take those observations and you feed them through GeoEvent Server into a dashboard. So here you see on a dashboard something that would be shared with management. As these observations are being made, they can see what the impact of the damage is, what people are observing. They might also have other feeds that come in. All of this is configurable without code. It's part of the platform. So how do you enable these things in order to take action with your community? That's really the key issue here. Imagery management. Years ago, you would be interested in getting an image, right? Finding that image, working with that. A lot of imagery is collected today. We have hundreds of satellites. FAA is saying, we'll have on the order of hundreds of thousands of drones. There's actually more drones in the United States now than there are airplanes, and that's growing very rapidly. A lot of sources for imagery. So imagery today, you don't get an image. Instead, you get hundreds of images, thousands of images, and you want to be able to manage those effectively and use them effectively. What the image management capability within the platform does is it allows you to treat all of those images of interest to you as one resource. So you're no longer thinking about an image, its neighboring image, its overlap. No, you just think about it as one resource once it's stood up and managed. And that's handled by image server. And that's what you saw with respect to the imagery over border. It's not only true for imagery, but it's also true for LiDAR as well. LiDAR data sets are managed the same way. Analysis. You'll find when you read our literature this concept of mosaic data sets. I'll warn you right now, they're mosaics or data set. They really are as image catalogs. But they're image catalogs that enable that idea of seeing entire collections of imagery as one resource that you are able to use. Attached with those is all the on-the-fly processing. What on-the-fly processing does is it processes just what you need when you need it. It's one of our design philosophies in building this product. Why is that true? Well, image collections are big in size. You don't necessarily want to process the whole thing if you don't need to. Over an image collection, what we find is that users often only use 1 or 2%. Any given user will use 1 or 2% of the image collection. So why process the other 98%? On-the-fly processing enables that for you. And it does two things. It saves disk space, but it also saves bandwidth. Of course, is an important commodity when you're trying to move imagery from the cloud back down to the user. What you get out of that is a variety of analysis products. So land cover, you'll hear more about that only. Vegetation health, useful in a variety of agricultural programs. Vegetation mapping, so on and so forth. Visualization and exploitation. We've also spent time trying to make it easy for you to exploit the data in very rich ways. As I said, we used to force the users into looking at imagery with north up in a map perspective. This is an oblique imagery that was collected by Digital Globe over San Francisco. You can see the buildings look like they're sticking out of the side of the earth, not very natural. You have the ability to switch to image space, and when you switch to image space, of course, everything looks intuitively pleasing as you would see it from an airborne perspective. But along with that, all the map features come with it. So think of it as the first image. The first image, we're bringing the map to the GIS. In this image, we're bringing the GIS into the image. And any other image that you would have would be mapped into this geometry. Along with that, you can do mensuration, measure heights of buildings, shadows that give you heights of buildings, etc. We talked just a minute or two about drones. Drones are making remote sensing very personal. Instead of having to wait for a large organization to go out and fly things, you can fly it yourself. You get nape imagery, you get it at 1 meter. If you buy premium services, you get it at 1 foot. If you fly a drone, you get 1 centimeter, or a fraction of an inch for your ground sample distance. Right? Extremely detailed information and imagery when you want it. This is an example of some of the data that was collected by one of our university partners. You can see that they collected a point cloud, they turned it into a mesh. It's now a 3D data set that they're able to utilize. And, they did this in a matter of hours. So they flew it when they wanted to, processed it, had it immediately available, extraordinarily high fidelity data. Of course, the downside of this is you can't collect a whole state at once. You can't collect a whole county at once. You can't even collect a whole town. But if you're focused on a very specific geography, it's extraordinarily valuable. The other thing is, the traditional approach is you collect imagery from maps, but drones are also used for inspections. And inspections of things that you can't easily get to. It's a particular case, a transmission tower, but it could be the side of a building, a roof, a variety of things that are not necessarily readily accessible. What do you produce from that? Well, with Drone to Map, which is a standalone app, by the way, but an app that's designed to be completely compatible with the platform. You can do base mapping, you can do site modeling, developing these 3D, very rich 3D objects, or you can inspect and measure depending on what you're interested in. The goal of this course is to provide authoritative data, and as a result, we have a variety of tools within the product so you can assess, is the data good enough for your needs? This is an example of a collection we did to validate the product. It was done in support of some work by the Corps of Engineers. They're doing monitoring of the sand on beaches, trying to determine whether or not they need to backfill, whether they need to dredge. 71 acres, processing time was 4 hours and 32 minutes. The root mean square error associated with the position of the points was 1.2 inches. Very, very good quality data. In fact, it was good enough that it compared to traditional transects with survey equipment or full LiDAR. So it's the world that's going to be evolving for all of us over the next few years. Photogrammetric workflow, of course, is to collect, make adjustments if necessary. Sometimes you have direct georeferencing, so it comes right off the sensor in good quality. Then process that data into whatever products you want, ortho, surface models, point clouds. But what we see is happening is people want this in the cloud. You'll go out into the field, you'll collect the data, you put it into the cloud, people 1,000 miles away do the processing for you, and then they redistribute it across all their constituents, which may be around the globe. So what you have for photogrammetric production, you've got Drone to Map, again, designed specifically for drones and very high resolution work. Ortho mapping within Pro, designed for everything, including drones, satellite data, airborne data, and now Ortho Map Maker, which is debuting this year. Standalone capability within the cloud to do the same. This example is another one that's doesn't get a lot of attention, but is very important. What we have here are green footprints, and these footprints represent imagery that was historic. It might be imagery from the 1940s, maybe more recently. The tools are there to build that into a base map for that epoch so that you have that to be able to compare it. And this is an example with the blue lines of the seam line generation. So we do full processing with seam line generation, color balancing, et cetera. So you end up with very nice, seamless base maps that you can distribute. Doesn't stop there. Think about 3D. Here's a colorized point cloud that's been turned into a 3D data set, and certainly it's very beautiful, but it's more than just a pretty picture, because with this technology you can also tie all your GIS data to the features that you have. So if you have information about what's in the buildings, what businesses are there, maybe even 3D interiors. You can take that 3D data set all the way into the interiors. And of course, we support LiDAR collection strategies, whether it be mobile, terrestrial, and aerial. Those are the foundation of what build a lot of these 3D data sets. They're also very important data sets if you're working with imagery, because you get this elevation information. Here's an example of being able to classify some of the buildings off the LiDAR data set. My point here is that think very creatively when you're working with imagery. If you happen to have LiDAR available, you can combine that with your workflows in order to enrich those workflows and get better fidelity of the output data. Finally, I just want to make a point of the fact that we've been working very hard to build our software in an open architecture. The index 3D scene layers are a good example of that. It's a data format that we produced over the years. And over the past couple of years, we presented to OGC. It's now an open standard. Very efficient. Lets you handle point clouds, mesh, 3D object models. And, when you think about remote sensing, I want you to think about, what are the possibilities that you can do with it. There's a tremendous amount of data that's freely available right now. We want to be able to process that into products that answer the kinds of questions that you have in the brain. And anyway, that's sort of concludes the overview of what I have. Next speaker is Emily. Emily works for Chesapeake Conservancy, and they've done a very fascinating project that really, I think, has transformed the way we think about remote sensing because it moves you from planning level data to actionable data. That I want to turn it over to Emily. Thanks.
Thanks so much, Jerry.
Yours, Emily.
All right, let me just share my screen. Can everyone hear me okay?
Got you loud and clear.
Okay, great. So I apologize again for not being there in person, but I'm glad I can join you remotely, and thank you all for having me. So like Jerry mentioned, I'm going to be talking about how the Chesapeake Conservancy is leveraging GIS and data for a healthy Chesapeake Bay. So first, a little bit about our organization. We're a nonprofit. We're based in Annapolis, Maryland, and the Conservancy mission is to conserve and restore the natural and cultural resources of the Chesapeake Bay, as well as to advocate for public access to parks and trails so that people can connect to the bay and enjoy it long into the future. So we are a relatively small organization, and we're working in a watershed of over 64,000 square miles. So like many of you, I imagine, as a nonprofit, we have to figure out how to really utilize our resources efficiently, and innovation is at the core of that. So we're always asking ourselves, is there a better, faster, more efficient way to do conservation to achieve our mission and goals? So I work within the Conservancy's Conservation Innovation Center, which is our team of about 11 geospatial analysts. And our goal is to really develop data sets and technologies to empower our partners with the information that they need to practice precision conservation. And we like to define precision conservation as getting the right practices in the right places at the right scale and making sure that they are working the way they're supposed to. So data and imagery really play a key role here. Like the LiDAR point cloud you see here, they really allow us to help our partners virtually walk the streams when they can't actually go out and walk all the streams in the watershed. And it really helps support science-based decision-making so that they can amplify their positive impacts on the ground. So in this presentation, I want to go through a couple of our foundational data sets that really enable precision conservation. And then I'll also go over some of our web-based tools powered by Esri products that help us prioritize where to work and also gain powerful insights from our data. So first I'll talk about our high-resolution land cover data. So as part of our partnership with the Chesapeake Bay program, we created a high-resolution 1-meter land cover data set for the entire Chesapeake Bay watershed. This data was released in 2016. And land cover, as Jerry mentioned before, is a representation of features on the landscape. And it's broken down into categories so that each meter by meter cell across the landscape is categorized as a cover type. So we have things like tree canopy, turf, agriculture, impervious surfaces, structures, etc. And knowing what's on the landscape is really important for us because it helps us establish a baseline, helps us identify areas for improvements, for restoration projects, and then we can also start gaining insight into how much pollution is contributed from different areas. So for example, we're more concerned about agriculture and impervious surfaces versus forested lands because of the potential for pollutants coming off those land cover types and contaminating runoff into our waterways. And then we can also start targeting where to do restoration projects based on how much pollution loading could be reduced. So to create the high-resolution land cover data, we integrated a variety of information, including NAEP imagery, that's National Agricultural Imagery Program, which is a 1-meter resolution. In some cases, we also included ortho imagery at the 6-inch resolution. We included things like a vegetation index with NDVI, as well as digital elevation model and digital surface model, both derived from LiDAR, where LiDAR data was available. And we used a rule-based classification algorithm to transform those data inputs into the various land cover classes based on their spectral characteristics. And then finally, we use ArcGIS to go back through an extensive QA/QC process to do corrections and incorporate planimetric data, so including things like building footprints and roads to get those really nice clean edges. I did want to mention we've more recently developed a methodology to do land cover classification all in ArcGIS Pro, which is really exciting. And in the future, we're going to be working with the Chesapeake Bay program to do updates on the Bay-wide land cover data sets, which will be really important so that we can start tracking and detecting change over time. So this image is downtown DC, if you can recognize it. This is the national land cover data set. So nationally available, considered best available before the high-res data. And it kind of just looks like a big red blob. But if you overlay our 1-meter high-resolution data set, you can really start picking out features. We know DC is super green, and you can see that reflected here. So this really gives us literally 900 times more information, whereas the National Land Cover data set is a 30-meter resolution to the 1-meter scale. So it really allows us a very clear picture so that we can plan on the parcel scale. And the high-resolution land cover data is also extremely helpful when we're looking at streams and waterways. So again, here you see the National Land Cover data set, and if we overlay the high-resolution data, we start picking out features like buildings, the subdivisions, and you can also see that we're picking up more tributaries to the river or stream there. And so this data really provides us with a much clearer picture of what's going on at the edge of the stream for our waterways in the Chesapeake Bay watershed. So next I want to talk about our high-resolution stream mapping efforts, which is sort of our second foundational data set that we use. So to do this, we start out with a LiDAR-derived digital elevation model, which gives us a very high-res picture of what the terrain looks like. The next step is determining which direction water flows across the landscape. So if you can imagine, if you dumped a big bucket of rainwater on a 1 meter by 1 meter square, we're going to be standing on that square and we're looking around at all the cells next to us to figure out which direction the water from the bucket is going to flow into. So we do that, iterate that across the whole landscape so we get an idea of how water is going to move. The next step is finding the areas where water accumulates. So that's based on how many upslope cells flow into any given cell. And then once we do that, we set a threshold. In this case, we use 60 acres of a contributing area. And any cell with that, that number of cells contributing to it, we're going to call it a flow path or a stream. Next, we determine stream width based on the drainage area and stream order. So we can determine, based on that upstream accumulation value, how big the stream will be based on some GIS models and regional curves. And then finally, we incorporate our land cover data into this as well. So that gives us a really comprehensive picture of where water is existing and flowing across the landscape. So how is this different? What you can see on the left here is the National Hydrography dataset, which has about a 40-foot positional accuracy standard. And you can see our data on the right-hand side. And what is really important here is the edge of stream. So when we're talking about planning a buffer, a riparian forest buffer along the stream, we're usually talking about 35 feet, which is sort of the minimum standard effective width. And so with the NHD data set, you can see that the 35-foot buffer is actually falling underwater. So the main impetus behind this, creating this high-resolution stream map data set is we really need that higher positional accuracy of the stream edge in order to effectively plan where we can put restoration projects along streams. So now I've talked about our high resolution land cover and stream mapping, but better data is only useful if it can really be leveraged to inform better, more cost-effective projects. So I want to kind of go through how we use this data to identify and prioritize best management practices to really maximize our water quality improvements. So most of our work on restoration has been focused on mapping areas where riparian forest buffers can be planted, like I was mentioning before, as you can see here in these example areas. And buffers are sort of established as a really cost-effective practice for managing and reducing pollutant loads to streams. The trees and the roots act as a natural filter for pollutants and runoff that would otherwise come right off of these agricultural fields and directly into the stream. And they also have a lot of great co-benefits, like providing fruits and nuts for harvest, wildlife and pollinator habitat, and they provide shade to streams, which is really important for trout and macroinvertebrates. So we know buffers are an effective way of treating pollutants. So I want to show how we go about mapping these buffer opportunity areas. So here you're seeing our high resolution land cover and the flow path data sets that I talked about. First, we kind of draw a 35-foot buffer area around the flow path, and we can identify gaps in riparian forest buffer coverage by looking at the land cover composition within those buffer zones. So the pink areas here are the unvegetated areas where you could potentially plant trees. And so you can see on each side of the stream here on the north and south side, you have relatively equal area project footprints where you could potentially plant a buffer. But how do we determine which one's better? a major driver of that decision is actually looking at the drainage area of that project. So we can put on our flow accumulation layers here, which is one of the intermediate data sets that I mentioned in our stream mapping workflow. And we can actually calculate the upland drainage area going to those project areas. So you can see here, you would probably want to prioritize installing a forest buffer on the south side of the stream because it has the potential to treat a much larger upland drainage area, and it's characterized by mostly agricultural landscapes. So, which means that it could have a greater potential threat from runoff of nutrients and sediments coming off those fields. You might also want to consider prioritizing this upland area as well for other best management practices. So you could look at things like grass buffers in the agricultural fields where you have concentrated flow, for example, or you could look at what kinds of chemical applications are being done on the field. Let's say there's a barnyard in the drainage area, you could look at manure management practices, potentially protecting the stream from cattle coming through there. So generally this area you would definitely want to prioritize and look at more carefully to see what's going on. So now I want to move on to demonstrating how we sort of package up all this information into web-based tools so we can really get it in the hands of people who can use it to implement restoration projects on the ground. So one example I'd like to highlight is a project that we did in central Pennsylvania. In 2016, we received seed funding from the National Fish and Wildlife Foundation to work with a variety of organizations that are all sort of working on restoration within a 4-county region in central Pennsylvania. So that's Center, Clinton, Huntingdon, and Lycoming counties, if anyone's familiar with the area. And we wanted to pilot a parcel scale prioritization, primarily focusing on buffer restoration in this area. This area is a really important place to work for the Bay as well as for Pennsylvania. There's lots of agricultural land use in the area. And of all the states in the watershed, Pennsylvania is the most behind in terms of meeting its pollution reduction goals for the health of the Chesapeake Bay. So our goal here in this project was to use data-driven methods to address the question, where can we really work across this region to reduce the greatest sediment and nutrient inputs to our waterways? So to do this, we first met with a network of restoration professionals in the region. So these included local conservancies, conservation districts, state agencies, to really collect their feedback and understand their on-the-ground knowledge of what's important to restore in these areas. And through an iterative process, we had multiple meetings with these stakeholders, and we narrowed down to 5 key attributes of a potential project that would qualify it as a very high priority area to do restoration for water quality. So we prioritized parcels that were on or upstream of an impaired stream segment, and even more so if it was due to agricultural impairments. We also prioritized areas that were on exceptional value or high quality streams. And then we also prioritized parcels with large drainage areas consisting of a lot of agriculture, impervious surfaces, and turf relative to the size of the planting area. And then finally, we packaged all that up into sort of an easy to use online web map for our partners. So this is what the web app looks like. I built this using ArcGIS Online and Web App Builder, so no coding experience required really. You can see all the prioritized parcels in the region on the home screen. And they're symbolized by tiers, so that the orange and yellow are sort of the highest priority areas. So the data layer options are on the right side, including many reference layers. You can type in an address in the geocoder, So if you zoom in, click on a parcel, you can get a pop-up window of its attributes, including all the metrics that went into the parcel score and the tier level. And you can also get owner information as well. You can see the restoration opportunity areas and the drainage areas on the parcel, looking at those layers, as well as the flow accumulation layers you see on there in light blue, so you can get an idea of how water is flowing across the property. And if I'm a restoration professional, let's say I'm about to go do a site visit on this property, I want to be able to make a map and print out all this information. So I can do that by using the select widget and the print widget to generate a printable PDF report that I can take with me. And this is a great sort of conversation starter with a landowner in a lot of cases. So the tool also, let's zoom out a bit and just look at the Half Moon Creek stretch. Let's say I'm working in this general area and I want to view the predators parcels in a table format. So I can do that. I can sort by attributes of interest. So let's filter by the map extent and sort by score. Then I can select the rows at the very top and I can be taken immediately to the top scoring parcels within my field of view. I can also use the table view to do filters. So let's look at only tier 1 and tier 2 parcels. Again, this sort of allows me to spatially hone in on the top properties in the area. And then again, I can go in and get information about the address and the owner to really target my outreach in this area. So finally, I want to go to a quick demo of how we've started using insights for ArcGIS to really take a deep dive into our data and understand the trends and patterns that we're seeing a little bit better. So Insights is Esri's web-based data analytics dashboard where you can create maps and charts like the ones you see here. Go ahead and start this. So you can see the parcel map prioritization again, and if I zoom in and select a parcel, the map is actually linked with the chart on the right, which is its score distribution chart. So I can easily see where this parcel's score falls relative to all of the others. If I select a top score on the chart, the map highlights it. I can zoom in to investigate further. Here again, I can view a pop-up box to get all the metrics that went into the scoring and prioritization of this parcel. And summarizing data is a simple drag and drop within Insights. So let's say I want to build a graph of the number of parcels in each county by tier. So I can pull those into the chart area from the data bar on the left, make a stacked column chart. And now I can see the breakdown by county. And if I click on any of the stacked bars, you can see that selection reflected in both the map above and the score graph on the top right, which is pretty cool. Let's say I also want to know how many total acres of restoration opportunity area, drainage areas, what's in that drainage area, so ag, impervious, and turf by county. You can drag those attributes into a table format, and it neatly summarizes the totals by county. Also dragged in here the score by county. Right now I'm just sorting by attributes of interest, and I want to change the score to average, and I can see that from my sorting, Center County is up at the top when it comes to total restoration opportunities, as well as top scoring parcels. So Insights also lets you do some basic spatial analysis. So on the right here, I've used the spatial filter function to pinpoint which parcels intersect with the contributing areas of impaired stream segments. So we've started to take this prioritization even a step further by strategizing outreach among communities where you could potentially turn an impaired stream back into a healthy stream by just focusing implementation on a handful of properties owned by maybe a dozen or so people. So this is allowing me to visualize that. I can go in and get owner information of those parcels within that catchment area. The best part of Insights, I think, is the interactive nature of the charts and graphs. So what I'm doing now is filtering by tier, and I selected just tiers 1 and 2, and all of the maps and graphs automatically update to reflect the data that I want to focus on. I'm just going to turn that filter back off. And so Insights is a really flexible interface for us to start being able to explore our data further and really easily share these results with colleagues and partner organizations as well. All right, so in summary, GIS technology really enhances our conservation mission. We've created high-resolution data that supports precision analysis and planning. We use Esri web-based platforms to provide user-friendly tools to our partner organizations, many of which do not necessarily have GIS experience or capacity, so they really need to be able to interact with the data and understand easily how they can use it. And all of our GIS work supports programs that really incentivize performance over effort. So an acre of tree plantings on one side of the stream shouldn't really be treated the same as an acre on the other side necessarily, because the landscape context matters so much. And so we really believe that the science of where is critical to accelerate our progress towards a healthy Chesapeake Bay and a watershed that ultimately we can all continue to enjoy into the future. So that's all I have. Thank you so much for having me. I'm not sure if I have time to answer a few quick questions or not.
I think so. All right, well, thank you so much for joining us remotely and for a great presentation. Right,
thank you.
Yeah, thank you.
Emily, could I ask you to briefly stop sharing? It's not gonna.
Oh. Yes.
Thank you.
Thank you.
Okay. Alrighty, how's everyone doing?
Good.
I'm Alberto, and I'm the last thing that stands between you and some food and drinks. I'd like to thank everyone for making it out here on one of the crummiest days we've had in recent memory. So props to you all for sticking around and for coming in the first place. Again, my name is Alberto Nieto. I'm a solution engineer at Esri, and we're going to talk about machine learning. But before we do, I think it's worth actually getting into some fundamental basics and make sure we dot our I's, cross our T's, and cover some fundamental information that I think is important before we get to that point. I also like to bug everyone I speak with and ask as many questions as I can. I'd like to ask raise of hands, how many people consider themselves analysts? How many people are GIS analysts specifically? Okay. How many people have used machine learning? How many people know how machine learning works? Okay. So I see like maybe this cluster of 5 people just raising their hands over and over again. I'm wondering what the rest of the folks do, decide or volunteer, etc. I'd love to learn about you guys. So my first question to you all is something that hopefully doesn't really need too much explanation. Maybe a lot of people already know the answer to this or know the value here. But what I want to ask first is, why do we need spatial analysis, right? Before we even get to machine learning, why do we even start with spatial analysis?
And it's always this idea of having data versus information, right? This concept of extracting actionable information out of data. We have a lot of data that we work with. And I'm going to post a few simple questions as well. If you have a spreadsheet of 100,000 records, are you looking at data or are you looking at information? Data, right? It's pretty easy to say it's just data. You're not going to hand a spreadsheet of 100,000 records to a decision maker and tell them to make a decision. You're expecting more, right? However, what if you make a map? How many people think it's data? Raise your hand. Let's say that every record in that spreadsheet had an address and you just simply plot it on a map. So one person, I think okay, a few people are saying you're getting into information. How many people say it's still data? Okay, so some people raise their hands both times. I think Celine did it in the back. And this one is definitely tougher. I think you definitely start putting your foot in information, but the argument actually is made that you're still just looking at data, that you can go beyond just putting points on a map and do more. So just like with spreadsheets, the way that you can perform some operations to get information out of a spreadsheet, you can do the same with maps, right? You can perform operations to extract meaningful information and get to interesting insights. And how do you do that, right? That's the million-dollar question. If you could do this easily, if you could do spatial analysis easily, everyone would be doing it easily. A lot of people do it well, though. So the one thing that I do want to say is spatial analysis is a messy, exploratory exercise that is very specific to every single domain. And perhaps that goes without saying, but there's no one formula that applies wholesale to every single problem. You have to get your hands dirty, look at your data, ask questions, fail, ask questions, fail. Eventually, after enough iterations, you'll get to a point where you've actually found something useful. But one thing that I do like to start with, at the very least, is this thing at Esri that we have that we call the language of spatial analysis, which is this progression of complexity where you start with basic assessments of where observations reside. You start measuring the distribution, the size, the shape. You perhaps start to understand how things are related. You look at relationships between different observations or different disparate data sets, right? You maybe look at locations and paths, so origins and destinations and the best path between those. And eventually you get to that ideal place where you can predict. You know something so well and you have such domain expertise and understanding of your data that you can even predict things, right? Or that you can quantify patterns that are just hidden in your data. That's kind of the golden key that everyone wants to find. And that's where you get into this realm of the word soup of machine learning and artificial intelligence and all that stuff and all the ads that you see about this, solving the world for you and predicting for you. But I would say that, as fascinating as it is, really pales in comparison to you and human intelligence. So I do want to give it some due notice. It is fascinating, it is important, and the way we define it is that machine learning is kind of this new, not necessarily new, but it's this way that has become important in the past few years due to this mix, an interesting mix of vast quantities of data and vast quantities of computing power that kind of expose new capabilities to not just gigantic organizations, but to individuals. Anyone with a powerful laptop, or really not even that powerful, can spin up a model that can classify or that can predict, given the amount of data that they have and hopefully a good understanding of a problem. And the way you define machine learning, broadly speaking, is these techniques that learn from data or that essentially have enough data and samples and enough distribution of the data that they can give you some information that you may actually use, right, for your problem. And they, broadly speaking, leverage just this vast quantity of data to get that done. These are not new things, by the way. These have been around for several decades. It's just this new, interesting mix of computing power and data that makes it kind of all the rage nowadays. Now, what we want to bring into this, though, the interesting part in my perspective is spatial machine learning, is bringing concepts related to contiguity, spatial distribution, proximity. And also, I think it's easy to understand how machine learning works in imagery, but I'm curious, how many people do vector analysis work, not just imagery? Okay, so only a few folks. The rest of the folks do imagery, I'm assuming? How many people do imagery analysis? How many people don't want to raise their hands at all today? Okay. All right. So I think it's worth mentioning that there's a number of tools in ArcGIS that have applied machine learning concepts or are starting to apply machine learning concepts, both in the imagery side and on the vector side. And one of the most elegant ways in which we can use machine learning in the platform are sort of subtle, elegant ways that are hidden. For instance, when you open up a geoprocessing tool and it determines the right parameter for some data set, because of the data set itself, that is extremely useful to the typical analyst. That's not flashy, and that's not saying, it's not like the commercial from Microsoft and Common saying that it's going to predict everything in the world, but it is elegant and it's useful to the analyst. It's able to help the analyst get to some answer faster, right? And there's a lot of tools that do that inherently quite well. There's also a second half to this story, which is we're not going to be able to bring every single algorithm that exists out in the world into ArcGIS. We don't have enough developers, enough resources. And specifically with these interesting things that are happening in deep learning recently with TensorFlow and PyTorch and scikit-learn, there's an interesting way to integrate those solutions into ArcGIS through our APIs. So if you happen to know some Python or enough Python to understand our APIs, it's actually quite, I don't want to say easy, but it's straightforward actually to conceive of a solution where the algorithm exists outside of ArcGIS, but because you need that capability, you can integrate it easily into a solution that includes ArcGIS. So some of the examples that we'll show you have to do with that integration. It doesn't have to be just tools that we have. It can be tools that exist somewhere else. That's okay. As long as it helps you, and if you need it, we can help you integrate it. So I think it's worth mentioning that ArcGIS does fit into this word soup of machine learning, but this word soup matters much less than this, right? What question are you trying to answer? What kind of things are you focusing on? And if they do need machine learning, great. If not, that's great too. So we're going to take a brief tour of some demonstrations. We'll make it fast so that you can get to the food and drinks very quick. But I'm going to show you 3 types of use cases and 3 demonstrations for classification, clustering, and prediction. And they're not all going to be imagery-based. Some of them are going to be vector-based. But the idea is that there's more behind the scenes. If you are interested, you can keep exploring and keep talking to us because we love to talk about it. So we're going to start with prediction. And I think this is the easiest one to understand, but probably the hardest one to actually do, right? Using the known to estimate the unknown. It's what everyone wants to do with machine learning. And what I'm going to introduce is a tool that we just released with ArcGIS Pro called Forest-Based Classification and Regression. And we wanted to call it Random Forest Classification and Regression, but it was trademarked. And we found, I guess the product team found that out about a week before they were about to release the tool. So they had to change all the documentation and all the tool and the GUI and everything, which was interesting. But with predicting, you have to, one of the ways in which you can predict is you can build these models that have explanatory factors. Like in our older regression tools, you basically bring enough ingredients that help, that are correlated enough with some factor you care about, that they explain that well enough to let you estimate in some unknown location, right? So what's interesting about forest-based classification and regression is the way in which you can bring these ingredients. Typically, you always work with attribute tables. Like if you look up a machine learning book, going to say, bring a table and do feature engineering and add all these attributes into that table and then do regression, do prediction. But in this tool, you can bring proximity inherently into your analysis, or you can bring rasters into your analysis. And it's going to use those very intuitively to build your model and to let you predict. So here's my example. We're going to take a look at home sale prices using spatial factors. And the way this works is we're actually going to take a quick trip to a county in Ohio called Summit County. This includes Akron, Ohio. Has anyone been there before or driven through it? Okay, very nice. Only about 4 people. So in this county, we have a data set of parcels. And all of these parcels have the typical attributes that you may expect if you're shopping for a home, such as the amount of bathrooms, the amount of bedrooms, the square footage of the home, the year the home was built in, the year it was remodeled in, all of that stuff. And if you look up a guide to perform prediction with machine learning, they will often reference a data set like this of take a look at all your homes, use all, do feature engineering with all of these factors and see which ones are best related and then predict. But what I want to bring into play is not just those factors. And by the way we're going to predict is using training data. We're going to use a subset of all of these parcels. Let's say that you conducted a survey to gather home sale values, or you have a limited data set of home sale values. But the ones in blue contain home sales. And those are going to be the ones that we use to build our model. Only about 5% of all the parcels in Summit County. But as we're building this, what I want to compute is not just using those attribute values. I want to I want to build the model using calculated distance variables. So in this case, what you're seeing is the parcels and the distances to golf courses. So if we think that golf courses are really important to Ohioans, then that could be a factor. There could be distances to railroads, and this actually, from personal experience, matters quite a bit. My wife's mother lives in Worcester, Ohio, which is pretty close to this, and in the middle of the night at 3 a.m., a railroad woke us up. And I thought at that moment, this is a terrible idea to live here. So I would conceive that this might be important if you're thinking of wholesale prices. Distances to highways or distances to highway noise walls could be important. And the way you bring those into the tool, let's actually take a look at the tool. It's a geoprocessing tool. There's going to be 3 categories of explanatory variables. So first of all are the training variables, and these are tabular variables. But to bring in your training distance, all you have to do is drag and drop the layers containing your training distances or your features that you want to calculate those distances to. So you can drag and drop your layer of golf courses as a training distance feature. You can drag and drop your railroads, etc. But once it's done building all of that, let's actually take a look at some of the outputs of one of these tools. There we go. When the tool operates, you're going to get a lot of messaging. And whenever you regress, and I apologize, this is very small, so I'll explain it out loud. One of the things that you're going to focus on with regression is your R-squared, right? And with this example, what was interesting is that you get an R-squared of 0.89, which was higher than by just looking at the literature examples that just look at those attribute factors, not the proximity factors. And more importantly, you also get a chart that gives you a view of which variables helped your model the most. Let me actually, I'm having trouble reaching that due to my taskbar, so let me remove auto hide and we can get there. There we go. Okay, so now I can take a look at this chart and it'll take a look at those factors that helped you predict, and it'll rank them by which factors helped or hindered your model the most. And in this case, noise walls, the proximity to the highway noise walls were the best factor to help predict. Interstates, proximity to interstates, proximity to railroads and golf courses mattered a great deal as well. So those proximity factors, who would have known what real estate location mattered? But it did, at least according to this. So that's one example of machine learning, right? Prediction. The next one, you've actually seen quite a few examples of this already, classification, or the process of deciding to which category an observation should belong to using training data or using a history of known observations and categories. And one brief thing I want to introduce you to, I work with the Department of Transportation quite a bit, and I'm going to introduce you to the exciting world of pavement cracks. So there's 3 types at the very least, but there's more. If you want to get into this exciting world. The first one is longitudinal cracks. There's also lateral cracks. And then I went to the University of Florida, so I love alligator cracks. But briefly speaking, there's this tremendously exciting job to collect data on all of these cracks on all the roads in the world, or in the country, and actually the world too. And my first exercise as an Esri employee was to go meet the Department of Transportation, and they showed me this fascinating workflow where they have these sheets. They drive down these roads in vans at 20 miles per hour or less. They record where these distresses are, the mile marker, the type of distress. It's mind-numbing, and it is depressing. And I remember that we were able to help them kind of digitize a lot of these features using field applications, and that was great, but it was still very manual. Because think about it, in this workflow, you don't just do this, that's mind-numbing enough. You have to get back to the field office or to the home office and then digitize all that in your GIS. That's terrible. So, yes, what if...
It's not boring. Pretty tracks are
Point taken. It's not boring. It's tremendously fascinating job. A tremendously fascinating job. So something we wanted to explore is if we could use a machine learning algorithm to detect these faults automatically as much as we could. And in this example, I'm going to briefly switch gears to a Jupyter notebook. How many people do some Python here? Nice. The same 5 people, same 3 to 5 people that keep raising their hands. So what I'm going to do here is run a quick model, and to show you the interpretation of the imagery by this model, we're going to run a video. So this is a vehicle driving across the Chesapeake Bay Bridge tunnel. And as it drives across, there's a small window that basically shows you the interpretation of this activity by a model built in TensorFlow. So this model was built outside of ArcGIS. And the different bounding boxes basically give you where the model has some level of confidence that there's a stress there of different types, right? And as the video speeds up, it's a little bit choppy here through screen share, but hopefully you can see that there's a lot of faults being detected of different types and labels. This isn't advanced spatial analysis, but it is important data generation for hopefully spatial analysis. And as this is processing, then through one of our APIs, we can connect it to ArcGIS. So I'm going to close this, and I'm going to show one of our applications. This is operations dashboard, and we're now looking at the outputs of that field data collection exercise, but this was now done automatically rather than through the sheets of paper. And if I click one of these features, we can click the attachment, you can see the collected images. This can be quite important. It's perhaps not going to be like professional LiDAR tracking of distresses, but in countries where you don't have a lot of resources to even generate a good data set of road damage assessment, this can be a good pass because all you need is a smartphone connected to your dash cam and enough people that can drive around and gather that data for you. At least they don't have to do it at 15 miles per hour with sheets of paper. So that's another example of classification, but I do encourage you to take a look. There's also some geoprocessing tools that we've recently released to facilitate this type of activity. One geoprocessing tool lets you build training data. It's called export training data for deep learning. And the other one lets you consume external models, such as the TensorFlow model that I just showed you, on your raster imagery. And that one is called Detect Objects Using Deep Learning. That's actually upcoming in an upcoming release. My final example is of clustering. And this one I find the most fascinating, actually, and most useful, but maybe hardest to explain. And this one is how you can group observations based on similarities of values or locations, but it's really useful to explore. So the typical ask that analysts get is, find me some information out of this data. Find me some patterns that matter in this data. And if you try to kind of break that down, typically what the person is asking for is, find clustering in this data, find the inherent patterns in this data so that we can ask better questions than just find some patterns. And the example I'm going to show is actually going to show a new capability coming up in ArcGIS 10.7. So I'm going to briefly start with some analysis that we've shown in one of our plenaries before. This example also has to do a little bit with real estate. This is Pittsburgh, Pennsylvania, and the problem that we're trying to solve here is that, let's say that you're a company that wants to open up a new restaurant. So one of the things you may do, obviously not the only thing, but one of the things you may want to start doing is by loading a data set of existing restaurants and trying to find patterns in the distribution of all of this real estate in Pittsburgh. So a very quick thing you can do is to cluster these restaurants. And let's actually take a look at the tool that I want to use to cluster. I'm going to go to Spatial Statistics, Mapping Clusters, and the tool is called Density-Based Clustering. And briefly speaking, what it does is it's going to take an input point data set and separate it into either observations being part of noise or clusters. So I'm going to show you the outputs of that tool. And there's 3 algorithms that it applies. One of the algorithms called HDB scan is really useful because it kind of defines what a cluster is at different spatial contexts through your data. So in dense areas, it'll say that a cluster is actually one thing, but in rural areas where observations may be more sparse, it'll redefine what it means to be a cluster there for that context. So a useful thing with new data could be to run density-based clustering so that you can kind of see those inherent patterns, spatially speaking, of your data. And then you can perhaps run something like standard deviational ellipses to kind of convert these restaurant clusters into zones, right? And those zones can be the target of further analysis. You could then create a chart of your total sales per zone, and then select maybe your areas that have the most sales. Let's turn this off so that we can see it. And then those could be perhaps the first areas that you start focusing on when you're doing prospecting. Now, apologies. I mentioned that we were going to show a new capability. And that capability is this concept of a hosted notebook. So if you do Python work, a lot of people use Jupyter notebooks to do their Python development or data analysis. If you do use Jupyter notebooks, typically you have to install them outside of ArcGIS and do the work there and then bring it back into ArcGIS somehow. What we're bringing in with 10.7 is this concept of the ability to create in ArcGIS Enterprise not just a map or a feature layer, but you can now also create a notebook. And with a notebook, let's say we're going to title it demo. We're going to give it a tag of a demo as well. It's going to spin up this Docker instance, basically this contained environment with all these capabilities to let you explore data and do analysis. And this is a Jupyter notebook inside ArcGIS. This is an ArcGIS notebook, essentially. What's kind of cool, though, is that we didn't just create Jupyter notebooks. We also added some GUI to assist this process. So you can add content just like you typically do in ArcGIS Enterprise, or you can do analysis and bring in one of your tools, and it'll create a cell with the right call to the tool. Now, the reason I mentioned this capability with 10.7 as part of clustering is because we brought that example of finding restaurant clusters for retail site selection as a template that when you spin up a new notebook, you can start with some completed analysis and tweak it and modify it however you need to. So in this example, it actually has some multimedia to explain this process of how to go through this analysis. You can re-execute it on your own end. These are dynamic maps that you can explore. You can bring charts, etc. And then at the very end, you can provide the outputs to some web map or to an application. From the hosted notebook, you could automate the creation of an application as well. So this is a brief example and quite a few demonstrations that hopefully give you a sense of how we interpret machine learning inside ArcGIS. But really, machine learning is just one part of this gigantic equation, right? I think the progression of spatial analysis is perhaps a bit more important. And machine learning will definitely rear its head, and we should know where it's useful and where it's not. But it's really kind of not just about this word soup, more about what you guys focus on, what you try to answer, what you're solving, and that's what we want to learn about. We'd love to hear more. So thank you so much.
Thank you, Alberto. Thank you all for joining us and participating in all the presentations. We're here to hang out, enjoy yourselves, get a drink and some food, and we'd love to have a conversation from here. Thank you all very much. Thanks to our presenters.
Thank you.